In this question, algebraic structure is given as G comma plus, where G is the set of all 2 by 2 real matrices, and plus is the binary operation which denotes the matrix addition. Here we have to denote the nature of the given algebraic structure. First option is a groupoid, second option semi-group only, option C monoid only, and option D is it is a given algebraic structure is a group. Here the given operation is plus, which denotes a matrix addition. So here let us check if this operator satisfies closure property or not. So if we add any any 2 by 2 real matrices, we'll be getting again 2 by 2 real matrix. So hence we can say that plus is closure. Plus is closure. So we can say now it becomes groupoid. In a groupoid, the given binary operator should satisfy closure condition. So up to here we can say it is a groupoid. Let us check if that group satisfies associative property or not. We know that matrix addition is associative. A plus B plus C is nothing but A plus B plus C. So here we can say associative property is satisfied. So here we can say it is a semi-group. Semi-group is a groupoid which satisfies associative property. So up to here you can say the given algebraic structure is semi-group. Let us check if if the given algebraic structure contains whether an identity element or not. So here a identity element is nothing but if B is any identity element, then A plus B should be equal to A, where B is identity element. So here we can say these A here A's and B are 2 by 2 matrices. So here we can say B is 0 0 0 0. So here identity element exists for the given algebraic structure. So up to here we can say here it is a monoid. Monoid is nothing but semi-group plus one identity element should be there. So let us check if this contains an inverse element or not. So if A is if B if let us say X, let us say X is an inverse. So here A plus X must be equal to identity element. So here identity element is 0 0 0 0. A plus X must be equal to 0 0 0 0. So here X is nothing but minus A. So we can say here inverse element exists and it is unique, and it is so here inverse element exists. So we can say monoid, it is if inverse element also exists, then it is a group. So groupoid only closure gives groupoid. So groupoid plus associative property gives semi-group. So semi-group plus associative property, semi-group plus identity gives monoid, and monoid plus inverse element gives group. So here we can say the given algebraic structure is group. So here correct option is option D.
Following statements is true regarding post correspondence problem, that is PCP. Option A, PCP is undecidable over the strings in alphabet 0, 1 for any integer m greater than or equal to 1. Option B, PCP is undecidable over the strings in single symbol alphabet with equal lengths. Option C, modified PCP is decidable. Option D, none of these. So here PCP, there is a definition here. PCP means if you take two lists of strings, that is list A and list B, if list A contains the strings W1, W2 and so on WK, and list B contains the strings some X1, X2 and so on XK, then for any integer m greater than or equal to 1, if you can find out the set of integers I1, I2 and so on Im in such a way that Wi1, Wi2 and so on Wim must be equal to xi1, xi2, xi3 and so on xim. If you are able to find out these set of integers to satisfy this condition, then we can say that PCP has a solution. If a PCP has a solution for every instance of the problem, then we can say that PCP is decidable. Otherwise, PCP is undecidable. Actually, if you take a strings of different lengths, that is alphabet 0, 1 over m greater than or equal to 1, we can't have a solution for all the combinations because strings are of different lengths of different combinations. So option A, PCP is undecidable over the strings in alphabet 0, 1 for any integer m greater than or equal to 1, it is true. Option A is the correct option. Let us see how B is false. PCP is undecidable over the strings in single symbol alphabet with equal lengths. When you take equal length strings and a single symbol, same combinations of strings will come and we can have the equality of these combinations for any integers. So that PCP is decidable but is given as undecidable. Okay. Modified PCP is also undecidable. It is given as decidable. It is also wrong. Option A is the right option here. Which of the following is false? Option A, traveling salesman problem is NP complete. Graph coloring problem is NP complete. Hamiltonian path problem is NP complete. None of these. Here NP complete means if any problem can be solved using polynomial time and using non-deterministic algorithm, then that problem is called NP complete. It can be solved only by using non-deterministic technique, but it can be solved in polynomial time. That type of problems are called NP complete problems. So here traveling salesman problem is NP complete. It is a true statement because there is no deterministic algorithm for this, and the graph coloring problem is also NP complete. It also can be solved only using non-deterministic technique, and also Hamiltonian path problem. So none of the statements are false here. That means option D is the right option.